Okay, good morning, everybody. Let's get started. Uh, Let me share my screen. Everybody, can you see the homework set too?
Yeah, we can see it.
Okay, great. So therefore, your question was problem number 5, right? So a 220 microfarad capacitor is connected to the terminal of a single phase generator which feeds a load through a single phase transformer, and the load voltage is 1280 volt RMS. Calculate the generator active power if the power factor is 0.85 and the generator MVA rating is 3 times the capacitor's MVA rating. Consider the system frequency is 60 Hz and the load side winding terms is 2 times the generator side winding terms of the transformer. Uh, so what type of problem are you facing with this one?
Personally, I just don't know like what to do with the capacitor. I know it's connected in series along one of the lines, but I don't know what to do
No,
with it.
no, that is not connected in series. It is connected in parallel. I mean, although it did not say series or parallel, but you have to assume that that is in parallel. You you you
Oh,
you
if it
remember that in the class I was discussing the necessity of connecting a capacitor at the terminal of induction generator. So therefore, it should be in parallel, not in series.
yeah, I thought it was series because it said terminal instead of terminals instead of saying
Okay,
both.
yeah. I mean, from the statement, it did not explicitly say it is series parallel, but it will be in parallel. So, and then can you do that, or let me show you the diagram. Just a moment. Okay. I mean, it will be like that. For example, you have your generator here. This is the generator. Okay. And then it is single phase. I'm just drawing online. It is called a single line diagram. And you have a transformer here. Okay. And then it is going on. And then the load is connected. This is the load. And here is that capacitor. This is the capacitor. So, and then load voltage was given. Probably we noticed 1 to 80 volt RMS, whatever it is. And also it says the load side has 2 times the winding than the generator side. This means if you say this side is 1, then this side is 2. This means load side has 2 times number of turns as compared to the generator side. That is the meaning. So therefore this, I think this information is enough. And then generator has power factor value. This thing is given. So therefore question is find out the generator active power, P value. That was the question. And I think you notice what was the value? 220 microfarad, right? For the capacitor. So therefore everybody say this is the picture. So and I think then now this information is enough for you. Tyler, is this fine?
Yeah, I think it's okay now, personally.
Yeah. So everybody, this side, the meaning is that this side has, load side has 2 times of more turns as compared to the generator side. That's why meaning that if this side has 200, then this side has 100. That is the meaning on ratio 2 that the statement says. So and then the voltage is given. And of course, this is in parallel. And there is nothing between the transformer and the load. Assume that is the pretty close. Similarly, on this side, there is no other components. There is on parallel capacitor, and capacitor value is given. And then the question is power factor value was given, some number 0.85 or 0.95 something. What should be the active power of the generator if the megavar capacity, if the MVA capacity of the generator is 3 times the megavar capacity? So you have to find out what is the megavar capacity of this capacitor, how much reactive power it is consuming or providing to the system. That is the meaning.
Will you be available for questions after we give it a try later today?
Yeah.
Cool. Thank you.
Okay. Yeah. I think the deadline is tomorrow midnight, right? Yeah. So I'm saving this on, and you look. Okay. So now once again, everybody see the question is calculate the generator active power, which is the active power means the real power, P, and power factor is given. And then this statement is important. Generator MVA rating is 3 times the capacitor's megawatt rating, meaning that with this information, using the 220 microfarad capacitor, first you have to find out capacitor reactive power rating. And then I said, okay, express it in megawatt. Therefore, whatever you calculate in terms of var, then convert into megawatt. So therefore, generator MVA will be 3 times of that. And then I think rest of the informations are given. And then I drew the picture, and because it is already recorded, so you can see in the video as well if you forget the picture. I think now everybody is fine. You can do that. Yeah. Okay, so I am stop sharing this on. Let me click. Okay. Everybody now, can you see my screen, like various losses in the induction motor?
Yep, sure can.
Okay. So as you know that we were continuing the discussion about induction motor. So last class we looked induction motor working principle, and then especially the slip concept. That slip is very important, which is the difference between synchronous speed and the rotary speed or actual motor speed. So now moving forward, we like to know the induction motor efficiency. So how we can calculate the efficiency? So you all know that efficiency means it is the ratio of output to the input, output over input. But then input means output plus various losses. So therefore, if you compare with transformer has only copper loss and core loss. There was no rotating loss or no rotational loss. But because this is induction motor, it is rotating, especially its shaft is moving, so it has rotational losses in addition to that copper loss and core losses. So we have to take into account all the losses to calculate the efficiency. So therefore, everybody see, this is just the flow. I mean, you have to start from here to solve the numerical problem in order to find out the efficiency. So first is, motor input to the stator. You know that we have stator and rotor. Stator is equivalent to primary, rotor is equivalent to secondary. We discussed those things in previous class. So now, once you apply the motor input to the stator, stator, I drew that it's a circular body. It's a like magnetic material on which you are placing the coil. Therefore, through the coil, it will have copper loss. So that's why I have written stator copper loss. I mean, so when I am drawing a picture, then it will be clear to you. First, just look this one. And then stator will have core losses as well. And you remember that in case of transformer, I mentioned that core loss means eddy current loss plus hysteresis loss. So this is coming from the stator material, stator body. So therefore, once you apply the motor input, electrical input to the stator, you have to subtract two losses. One is stator copper loss, or another is core loss. Then the remaining power, I mean, after subtracting these two losses, the remaining power will be the power input to the rotor, or that is called the air gap power. Because there is no direct connection between stator and rotor, accordingly, it is called the air gap power or power input to the rotor. Therefore, once it is the input to the rotor, again, like everybody, I assume that the rotor is still a core material. It's a circular body, but it's a core material. So again, it will have copper loss because there are winding placed on the rotor, plus again, similar to the stator core losses, exactly the same thing, core losses. This is with the rotor. So therefore, subtract this rotor copper loss and core loss from the rotor power input. Then that thing you can say that is the mechanical power developed at the rotor. This means we are assuming mechanical power developed mean we are assuming that shaft has started rotating. That once the shaft has started rotating, this means there will be rotational losses like friction loss, bearing loss, windage loss, etc. Rotational loss. And then there is another loss, it is called stray loss. Stray loss kind of miscellaneous type of loss. It is called sometimes miscellaneous loss. But stray loss, it is very negligible. Typically like up to 2% or up to 3% of the total capacity of the motor. It's very small, very negligible. What is the reason? That is coming due to the non-uniform current distribution in the copper, distortion in the magnetic flux or the harmonic fields. So you know that although at the beginning you will be providing the sinusoidal input, but still in the process, in the stator circuit or rotor circuit, there can be some nonlinearity or some magnetic flux could be distorted or there could be some harmonics. So therefore there can be some loss, although that is small, what you have to take into account. That is called the stray loss or the miscellaneous loss sometimes. Therefore, after subtracting those two losses from the mechanical power, then that is called the shaft output power. So this is the actual output power which is available on the shaft, the body which is rotating. So therefore you see, everybody see the flow from here, motor input, and then this is the shaft output power. So this is the actual output power. I mean, sometimes in some books you might find that this mechanical power is called the output power, but that mechanical power, like before subtracting the rotational losses and stray loss, that's why actual shaft output power is this one, after subtracting the rotational losses. Therefore, when you will be solving the numerical problem to calculate the efficiency of motor, you will be finding out this one. What is the shaft output power? And then of course you need to know what is the motor input. Then this is the output over that input and taken as a percentage. So now, I mean, here it is kind of the flow. Like everybody, if you can just remember this flow, then it is easy to solve the problem. So therefore, let me take you to that whiteboard, then it will be much more clear to you. So everybody will be fine. Let me delete this thing. Okay. So everybody see, I'm drawing the big picture. So okay, so this is the stator body. Everybody see, this is the stator body. So at first, we are applying the input power. So we are applying the input power to the three phase. For example, this is A phase, this is B phase, and this is C phase. So here we are applying the input power, P in. So what should be the P in value? So P in, like you can say, that is very important. P in is, because this is three-phase system, so I have to use that three-phase system equation root 3 VL IL cosine of theta. Everybody see this one? P in root 3 VL IL cosine of theta. This means this VL is line-to-line voltage. So this is VL between two lines. So therefore that information will be given in the problem. So therefore you will be knowing what is VL and how much current is entering. This is IL. And of course, power factor information will be given. So you will be getting the cos theta. So therefore, by using this equation, you are able to find out what is my input power. So this is input power. Now everybody come back. So meaning that input power is available on the stator body. Now, because current is flowing through these coils, you see current is flowing through the coils, and we are assuming that this is not only just inductor, but also it has some resistance. Although it's small resistance, but each coil has some resistance value. So what will happen? You see, IL square R. There will be some losses. I square R loss. That is called the copper loss. So therefore, you see, you are applying Phi in, this is the electrical power. You can say power at the terminal, power available here. And when that power is entering into the coils, into the stator body, then you have to subtract this loss. And because it is three-phase system, it is like 3 times 3 IL square R. So therefore, once you get the Phi in, then from here you subtract this one. And then you see this circular body, this is the core material. So it has copper, it has eddy current loss and hysteresis loss. It has eddy current loss, hysteresis loss. Therefore, from the input power, you subtract this one, and then again you subtract that core losses. This means that eddy current loss and hysteresis loss. So therefore, after subtracting these two losses from the input power, then where that power is going? That power is going inside the rotor. This is the rotor circuit, you know. To the rotor, actually, that shaft is connected. So this body is called the rotor body. So therefore, everybody say there is no direct connection between stator and rotor. It is called the air gap. They are separated by the air gap. So therefore, and okay, let me draw the coils. So again, it has also three sets of coil, three-phase system. So therefore, come back here, P input minus this copper loss minus core loss. Now this one, after that, the result is the input to the rotor, Phi into rotor. That is the input power to the rotor circuit. So this means, so everybody follow the sequence. Then here you are getting the input to the rotor circuit, this result. And once you apply this on, so we discussed the working principle of induction motor voltage will develop on the rotor coils, current will flow, and the torque will produce another sets of flux. And because of the interaction of the flux, this shaft will move, but still the shaft has not rotating. So now come back. This is the input power to the rotor. So once it is input power to the rotor, then again these coils have some sort of resistance. Not big resistance, but there are small resistance. So again, from input power to the rotor, you have to subtract this type of losses, copper losses. Again, because there are 3 coils, it is kind of 3 times. So therefore assume that this is the rotor current, IR square, whatever its resistance is. You subtract, and again this circular body, this is a core material. So it will have again core loss. So again you subtract the core losses from there. That is the core loss. So then after subtracting the core loss of the rotor, that is the, you can say, the PM, mechanical power applied on the shaft. So mechanical power means then the motor has gained the energy. Motor has the enough torque now to rotate, and then motor has started rotating. So therefore before starting rotating, this difference up to now, I am calling that mechanical power developed up to now. And once the motor has started rotating, there is friction loss, windage loss, because this shaft is confronting the wind. So friction loss, bearing loss, and then as I told you, because the working principle, there will be a magnetic field here, and there will be another magnetic field here. There will be interaction. During interaction, there could be some non-linearity, some non-uniformity in the magnetic field. There could be some harmonics also. So we have to subtract, which we call the hysteresis loss. So therefore, after mechanical power, then again you subtract that friction loss, windage loss. You can say kind of the rotational loss. So once you, after subtracting the rotational loss, and then you also subtract that hysteresis loss. So after subtracting that hysteresis loss, this result, final result in the shaft output power. So therefore here I will write that thing, shaft output power. Yes. So this is my final output power. Everybody, could you follow me? Everybody is fine? So should I repeat it? Do you have any question?
So what exactly are the equations here that we need to look for? I see we have 3I squared R times the resistance R minus the core of the rotor. But I just, so that's how much power goes to the rotor is.
Yeah. So yeah, exactly. So therefore, I think everybody understand the first equation, right? The phi in √3 VL cos theta. That is at the very beginning. You are applying this power, the power input that is coming from the line actually. So that's why, and that power is entering into the stator circuit at first. So this is the like overall at the beginning, this is the input power. And then you are subtracting this on 3IL square loss, this on these 3 coils on the stator. And also you are subtracting the core loss of the stator. So, I mean, both stator and rotor has the core loss, and both have the copper loss. It is called the copper loss. Let me write. This is called the copper loss. This is called the copper loss. This one, 3I square R. And this is the core loss. So therefore, after subtracting core loss and copper loss of the stator, that is the thing I am telling that, okay, this is the input power that is going to the rotor. And then, so therefore rotor input, I mean, I can designate in that way. Let's say, let me write here, for example, phi of R. Phi of R means rotor input power. So therefore this pin is the input power here or input to the stator circuit. But then after subtracting this loss and this loss, it will be the input to the rotor, or sometimes this is called air gap power. Okay, you have to keep in mind, input to the rotor sometimes called the air gap power. Air gap power. So air gap power it is called because there is air gap between stator and rotor. So the air gap power means input to the rotor circuit. And once it is input to the rotor circuit, then again you subtract its copper losses, I mean rotor copper loss. And then again you subtract its core loss. That is the mechanical power Pm available on the shaft. And then with that mechanical power, it will start rotating. And once it will start rotating, then you have to subtract rotational loss, friction loss, windage loss, any other losses, remaining losses. Then you will be getting the actual shaft output power. Is this fine?
Yeah, it's clear.
Yeah. So therefore, I mean, just either you draw this picture to, I mean, it is, you will easily, you can remember. Either you draw that picture or you remember the textures that I showed at the beginning in the slide. I mean, I would prefer to go with this picture, then it will be, I mean, clear to you. Input power to the stator, that is the beginning, my start point, subtract stator copper losses, its core losses, then the difference is the input power or air gap power to the rotor. Again, subtract its copper losses, subtract its core losses. That is the mechanical power on the shaft. And then at that time, by then the motor has started rotating, subtract the rotational losses and stray loss or any miscellaneous loss. That is my shaft output power. So therefore, to calculate the efficiency, if you are asked to find out efficiency, this efficiency is power out over phi in. So therefore your output power will be this one, this shaft output power, the final output power. And then input is the actual input, auto your input. Yes, which was available here. And then it just to multiply by the percentage. So you will get the percentage efficiency. Okay, so therefore let's go back there and solve a problem, then you will be fine. Okay. Okay. So as I told you, either you remember this way in the text format, or you remember that diagram. Exactly. You see, this will be your stage. Input power, then those two losses, air gap power or input to the rotor, those two losses, then mechanical power, again subtract the remaining losses, rotational losses, final shaft output power. That is the flow. Therefore, now moving forward, everybody, let's have a look at numerical example, then it will be clear to you. Okay, everybody read this problem. A three-phase, two-pole, 480 volt, 60 hertz, 50 horsepower induction motor is supplied 70 ampere at 0.8 lagging power factor. Then I think I told always you will remember the motor is expressed in terms of horsepower. Always motor is expressed in terms of horsepower. And I mean the majority of the cases. Generator is expressed in terms of kilowatt, megawatt. Transformer is expressed in terms of MVA or kVA, we discussed. But in case of motor, always expressed, motor or any type of engine like petrol engine, diesel engine, always expressed in horsepower. And on horsepower is 746 watt. You know that thing. And the meaning of these lines, this is frequency, this is pole number. This 480 volt because this is three-phase system, this is line-to-line voltage. By default, you see, statement does not say that this is phase or line because nothing is mentioned. By default, this is line-to-line voltage. Everybody keep in mind, this is the like real practice. In real world, the rating of motor generator is expressed in that way. So therefore, this voltage, if it is three-phase system, by default, this is line-to-line. Don't consider this as phase voltage. Then you will get the wrong result. Okay, and the is supplied 70 ampere. Similarly, this current information, that is the line current, at a 0.8 lagging power factor. Because you know that induction motor, this is basically it has stator rotor, they have the coils, that's why the power factor is lagging. So 0.8, and then say its stator and rotor copper losses are this and this respectively. Can you see the information? These numbers are stator and rotor copper losses. That 3I square R that are showing. So this means you don't need to calculate. Those values are given directly. The core losses at the stator and rotor are 1500 watt each. This means that the same number 1500 watt is for both stator and rotor, the same number, the core losses. And then you see the friction and windage losses are 800 watt and the stray losses 200 watt. For a rotor slip of 3% at the rated voltage and rated frequency, determine the following. First question, what is the rotor speed for this motor? What is the air gap power? So air gap power means input to the rotor circuit, input to the rotor, not the stator, air gap power, the mechanical power developed. So when it is mechanical power developed, this means that you can assume at first you have to calculate input power, you have to subtract stator core loss, copper loss, then you have to subtract rotor copper loss, rotor core loss, then you will get mechanical power and the shaft output power. So we just discussed few minutes back. And finally, the efficiency of the motor. So therefore, this is the problem. This is the 5 questions, and then say how we are solving. So everybody say, let me make it much bigger. Okay. So everybody say the first question was find out the rotor speed. And then slip value was given. Slip was 3%. So to find out the rotor speed, you see, you need the help of the slip equation. So therefore everybody say, first I have written down the slip equation. Slip is ns minus nr over ns. Because it is rotor speed means this term, nr. Because ns is the synchronous speed. So you see that I am calculating here, ns 120 f over phi. So 120 multiplied by frequency 60, so 3600 RPM. I got this one. And then in the slip equation, substitute the values. So slip was 3%. This means this is 0.03 that I am plugging. And ns value you will get from here. So therefore, if you manipulate, then nr value is 3492 RPM. And you see, this makes sense. As in the last class, I told you that always there should be difference. And ns must be greater than nr for motor operation. For the generator operation, the reverse thing, this number will be larger than this number. I mean, later we will solve other type of problems. That time you will find if it is a generator problem, then nr value must be greater than the ns value. So therefore now this makes sense because this is motor problem. Okay, now come back. So the second question was, you see, what was the second question? Air gap power. So air gap power means input to the rotor circuit, input to the rotor. So therefore now everybody say, First, what I am calculating? Input power to the motor. That is my very first step. Input power to the motor. That is √3 VL IL cosine theta. That I was explaining you in the whiteboard. So √3, then VL value was, you see, those numbers are given at the very first line. 480 volt. Induction motor is supplied 70 ampere. This is the current value. And 0.8 lagging power factor. So 0.8 is your cosine theta. So therefore, see my calculation. I got 46,557.53 watt. I just express in watt. You can express in kilowatt, no problem. And then what will be then my air gap power? So this input power is overall input at the very beginning, which is going to the stator. But I have to find out air gap power, which is the input to the rotor. So what I have to subtract from here? So this number, and I am subtracting this as stator copper loss, and this as stator core loss. Therefore, now everybody read the statement. See, its stator and rotor copper losses are this and this. This means this number is for the stator copper loss. So from the input power, first I am subtracting this one, and then the third sentence, the core losses at the stator rotor are 1500 watt each. This means this 1500 watt, that is the core losses, the same for both stator and rotor. That's why there I am subtracting, you see, that number 1500. So therefore first number is stator copper loss, second number is stator core loss. So after subtracting, I got 40,800 watt approximately. That is my air gap power or input power to the rotor. Then the third question was find out the mechanical power developed. So then I am doing mechanical power developed. Now this is my rotor power, air gap power means input to the rotor, that power minus this number is rotor copper loss, minus again this number is rotor core loss. You see those things once again, those things were given here. This number was the rotor copper loss and this number is rotor core loss. So that's why I subtracted those two, and I got 38,300 watt. And that is the mechanical power. But then question number D was, what was the shaft output power? Shaft output power, and then finally the efficiency. So then how I am getting shaft output power? Again, from this number, I am subtracting windage loss, friction loss, and 200 was stray loss, miscellaneous loss. After subtracting those two losses, I am getting 37,300 watt. So that is my shaft output power. That power is available actually on the shaft. So then everybody say, I am calculating the efficiency. What I am doing, this is my final output, this number here. And what is this number? This is the input. Go at the beginning, input power, this number, which was the actual input power to the stator. And then multiply, I got 80.12. So everybody, could you follow me?
Yeah,
Yeah, I
makes
can
sense.
follow.
Looks good.
Yeah, I think if you just see this on and then on by on, or the diagram that I showed in the whiteboard, or if you can remember my discussion, then it is not difficult. I mean, easily you can solve. Just it's like couple of steps, but it's not difficult at all. Easily you can solve, I believe. So therefore, I think tomorrow you are going to return me the second set of homework, and then I do hope to return you both set of homework on Tuesday, both the first set and the second set on Tuesday. And then once you submit me the second set of homework, I will assign you the third set of homework, with this type of numerical problem, then easily you can solve. Like you have to find out rotary speed, this type of efficiency, and then few other stuffs on the induction motor. And then you all will be fine. And I think you are scheduled for your first midterm exam September 22 or September 20, something like that. So next week I will remind you and I'll discuss about that. So then everybody will be fine. Okay, so moving forward, you see that at least I think you could understand that induction motor is very similar to transformer. You see, stator is primary circuit of transformer and rotor is the secondary, and the working principle is the same. So that's why the way we discussed the equivalent circuit of transformer, today similarly, we will be discussing the equivalent circuit of induction motor. Again, it has exactly similar type of equivalent circuit. So, and then that equivalent circuit of induction motor is very important to analyze the system performance. How does the motor behave? What is its characteristics? To analyze that and to understand the motor performance, that equivalent circuit is important. That's why now we will be looking at equivalent circuit, how we can construct. Now, first you see that you all have to remember these two things. Probably you can remember in the last class I was discussing. What was the discussion? Under running condition of motor, rotor frequencies F2, S, F1. So this means before running the motor, both rotor frequency, stator frequency is same, which is F1. But once motor has started running or during running condition, this is the relationship. So when we will be drawing the equivalent circuit, you have to take into account this one, because we will be using this concept. And also during running condition of motor, rotor voltage is S multiplied by the previous voltage. Previous voltage means pre-running condition, before running condition, this E2. So this means that both frequency and then rotor voltage under running condition, you have to multiply by the slip. That is the catch point or the key point to remember. Now, based on that two concept, now let's move forward. Everybody say, oh, let me a little bit squinch. Okay, everybody say. This is figure 6.14 from the book that we are following. You see the development of the part phase stator and rotor equivalent circuit of induction motor. Figure A, top figure is for the stator equivalent. And then VCD, actually all are the rotor equivalent circuit in different format. So I am coming that gradually, then you will get fun. So everybody see the top one is the stator equivalent circuit. So stator equivalent means, if you remember the transformer primary side, exactly the same thing. So everybody look, we are applying the voltage to the motor, to the stator, current flowing is ion, and R1 plus J axon, this axon, that is the actual coil on the stator circuit. This is kind of per phase circuit. It is the same for the three phase, just it is treated one phase at a time. So R1, and then every coil has some sort of resistance, as I already mentioned, which is R1. So here you see the symbol 1 refers to the stator, and then later in these figures you see symbol 2 all 2 refers to the rotor circuit. Just keep in mind. And then once you apply the voltage, it will induce voltage on the stator circuit according to Faraday's law of electromagnetic induction. And then you remember this portion is representing that magnetization portion. So therefore, excitation current and something is going as core loss. So the core loss resistance component and the magnetizing component. So you remember exactly we showed the similar things for the transformer. So therefore you understand this thing. This is for the stator circuit. Now what about the rotor? For the rotor circuit, you remember that with the help of the induced voltage on the stator, then rotor voltage gets developed. Rotor voltage developed because there is a rotating magnetic field we discussed in the previous class. So the rotor voltage developed. So rotor voltage E2. But because we are considering the running condition, that's I see what I have written SE2. That is this one. Everybody say SE2 under running condition, not just E2. So that's why you got SE2 here. And then in the rotor coil, current I2 is flowing. This is rotor resistance. But everybody say what I have written here SX2. You see, when it was the state, see the difference. When it was the stator circuit, it has just JX1. There is no S here. Because that S slip is related to the rotor movement. Therefore, it does not matter the rotor is moving or not moving, motor is running or not running, that does not matter. You can apply the voltage to the stator, and stator is a standstill still circuit. So it is independent of the running condition, independent of the slip term. That's why in the reactance here, there is no slip. But here there is slip term. And then can you guess how the slip thing comes? So everybody, you know, what is the X? X2 means reactance. And what is inside the reactance? X means omega L, 2 pi FL. Remember, 2 pi FL. So therefore F, before running of the motor, it is just F. But once the motor is running, frequency will change. See the conclusion. Under running condition of motor, rotor frequency F2 S multiplied by F1. So therefore, when it is reactance X, X means 2 pi FL, so that F is getting changed, S multiplied by F. That's why you are looking the S here. And then this is resistance. Everybody, do you understand this thing, what I am telling? So far, could you follow me?
Yeah, I think so.
Yes, great. So everybody keep in mind, this is the rotor circuit under running condition. Rotor circuit under running condition. If it is not running condition, then I would omit the S from here and S from here. It will be just E2, I2, X2 and R2. If you assume the motor is not running, then okay. Then here you say, from here I am going here. Everybody see the sequence? Can you see that there is no S here? And can you see again here the difference between this one? There is no S here. But then what happened? It was R2 here. Here it is divided by S, by the slip. And I have given a variable sign symbol. Therefore, how I got that one? So therefore, for you, like I did that one. I wrote in like a PowerPoint file using a pen. I did that. Everybody look this circuit. This is a series circuit. It is resistance. This is reactance. This is the applied voltage. This is I2. What is my I2 expression? So you look, I2 is this AC2 over R2 plus JSX2. So you all understand this one. Then what I want to do from here, I want to make free E2. I don't want to see the S with it. That is my intention. So that's why what I am doing, I am dividing both numerator and denominator by S. I am dividing numerator and denominator by S. So therefore what I will be getting, see that one, it is cancelled. S is cancelled with X2, so JX2, but then R2 over S. Now you see, now I am representing this equation in the second circuit. Now everybody match. This is this E2, this is I2. My X2 is free. there it is independent of S, but here it is S, R2 over S. This is R2 over S. And I am putting variable sign because it depends on what is the slip, at what speed motor is running. That slip is the main governing factor for induction motor. That's why this is the variable sign. That's why if you see this book or any other book or any literature, any power meter book, for the rotor circuit, always you will see this thing. The S is not here, S is here. So, and then from there, sometimes in this book and some other books, you will be finding that this R2 over S is decomposed into two parts. You see, here it is just R2, and then here it is R2 into 1 minus S over S. Therefore, if you just sum up these two, R2 plus this one, ultimate result will be R2 over S. Therefore, sometimes this representation is also used. Someone say, okay, no, let's decompose this into two parts. Just make one variable resistance here, and then one component is like that together with the S. But you don't need this one. If you just remember this format, that is fine. So this means that if you are asked to draw the complete equivalent circuit of induction motor, then first you will be drawing this one, and then here you will be attaching this portion, I mean the C. You will just connect the C portion here with it. That will be your total or the complete equivalent circuit. Everybody, could you follow me?
Yep.
Yeah. So therefore, just this thing, I mean, you are fine with the stator, As I told you, it does not matter the motor is running or not. You can apply the voltage to the stator. It does not matter because stator is static. That's why you are not worried with any slip term here. You see, nowhere you will find any slip term. But the only you have to make worry or you have to pay attention once it is rotor circuit. Is it before running or after running condition? Whether motor is running or not. If runs, then the slip thing will come. And that is the reason you will find R2 over S. So it is hugely dependent on the slip. That's the key. So therefore, as I said, you might attach this thing here. So if you attach, then that will be a complete circuit. And then, so for example, here I have shown exact equivalent circuit with the core loss resistor omitted. So you see that portion, and then that is the rotor side as I told you. But here you see, here I am showing only XM, and that is the title, the figure caption, with the core loss resistor omitted. As I told you before that this is basically the core loss, and this is very small. This is very small. So this is main dominating, that magnetization effect, because induction motor is working on the magnetization principle, same as the transformer. That's why this portion is very important. You might neglect this one. You might neglect. That's why again, in some book, in some power book, or you are listening someone's lecture in some conferences or in symposium, you frequently you say they are neglecting this portion. That is this circuit. You cannot say, but you have to represent this one. You have to show this one because this is the representing magnetization. And you see exactly, as I told you, that the air gap, I mean, main input power after subtracting these losses, then this is the air gap here, and then that air gap power is going to the rotor circuit. So that's why exact equivalent circuit with the core loss resistor omitted. So now, if I ask you in the exam, okay, just draw the complete equivalent circuit, then you just connect this on here. You may not need to omit this one. I mean, including this one, you show me. Yeah. Unless I say, okay, omit the resistance. You show this one, the complete diagram. I think everybody understood this thing. So then moving forward, I'll be discussing few more things today and then I'll stop. One thing is called soft starting of induction motor. This is one concept. Soft starting of induction motor. So what does that mean? So what I've done, in order to reduce the initial transient or high inrush current, an induction motor is started with a small reactor, which is called soft starting. So probably you could remember, in case of transformer, I was discussing about the inrush current, high inrush current. Can you remember that I told that if you suddenly energize a transformer with three-phase lines, then the current goes very high. Transient happens, then subtransient, and finally it goes away. But initial current could be 8 to 10 times or even much higher than the rated value. And then we connected a reactor. The same thing. In case of induction motor, during starting, you have to connect a small reactor, a small inductance value. And then if you do that, then you can mitigate or you can eliminate those initial transient or high inrush current. That is called the soft starting. So therefore, to explain it clearly, let me take you to the whiteboard. Okay, so everybody, let me clean off this picture. Okay, so therefore, once again, like what we are doing, this is the stator. This is the stator, and what we are telling that these are the lines, three-phase lines. Of course, this is the stator. So I'm not drawing the rotor. I don't need to draw it. And then you will be applying the voltage or current here, but then the actual lines are here. These are the actual line, like line on, and then here it is, sorry, this is line 2, and then there is another line here. This is line 3. So therefore, this is your induction motor. This is your induction motor. You want to run it. So that's why first you need to power the motor. This is your three-phase system, just A phase, B phase, C phase. Okay, then you connect it, you energized it. Of course, 3 switch at a time. If you do that in that manner, then the current, that the rotor current, sorry, the stator current, initial current, you might say very high value. For example, if this is its rated amount, it should be the current magnitude from here. But because of this nature, because of suddenly switching, suddenly energizing the 3 lines, then the current value might go very high. And then gradually it will settle down. So therefore, this is called the inrush current or initial transient current. That thing will happen if you do in that manner. So, and then that is detrimental for the circuit, because very high value will flowing is going to the coils, stator coils. These coils might be overrated and might be immediately burnt. So that's why it is not advisable to close the circuit in that manner. So then what you have to do? Therefore, before closing, first attach some sort of a small reactor. There will be some reactor circuit. There will be some reactor. I mean the inductance. Once you have the inductor, and then you close. So therefore, these are the L. These are the small value of L. So therefore, how it will mitigate the transient? So you all know the function of the L. It impedes the rate of change of current. Current through the coil cannot change immediately. So that's why there can be some transient, but very small. Maybe it will be like that. It will go ahead, then immediately it will be mitigated. So then these coils are safe. So therefore, in the lab, actually you will be doing this one, but you don't need to do anything. This is inbuilt. You will directly close the switch. So you are fully fine. So therefore, in our laboratory, those induction motor, this property is inbuilt. It is the soft starting. So you will not face any problem. But just I am explaining the phenomena that what actually happens in real practice. So this is called the soft starting. This method, the starting of induction motor or energizing the stator with the help of a small reactor, is called the soft starting. It is called the soft starting of induction motor. It is the soft starting of induction motor. So everybody, could you follow me?
So far,
this-
so good right now.
So sorry, what you said? You remember that we discussed the exact similar things in case of a transformer.
Yeah.
Exactly
Yeah,
the
I remember this. Yeah. Mhm.
Yes, exactly the same thing. Yeah. So in case of induction motor, it is frequently called the soft starting. Soft starting means the safe starting that will mitigate the transient. Okay, therefore I am saving this on, so you can see later in the video. Okay, then again go back there. You see, that is the thing I have written. In order to reduce the initial transient or high induced current, an induction motor is started with a small reactor. This is called the soft starting. Okay, now I have written two more things. Typically, rotor rotates in the same direction as the stator magnetic field. So this means that we are applying the voltage or current to the stator at first. And then you remember I told, okay, it is producing rotating magnetic field. If it moves clockwise, that magnetic field, with the speed ns on 20 f over p, if that moves clockwise, then rotor will also move clockwise. If the stator magnetic field moves anti-clockwise, then the rotor will also move anti-clockwise. That is the meaning. Therefore, in this case, the stator magnetic field direction is the dominating, that is the governing, that is the driving. Therefore, rotor rotation or rotor movement will follow the direction of the stator movement of the stator magnetic field. That is the meaning. So therefore, and then what I said, the direction of rotor rotation can be changed by interchanging connections between any two lines. So therefore, what does that mean? For example, you notice that for a motor, for induction motor, the indicated or the prescribed direction is clockwise, but you are noticing that it is rotating anti-clockwise. Then immediately you have to stop the motor and you have to interchange or you have to swipe any two lines. Then the direction will be fixed. So this means that, like, again, let me take you to that whiteboard, then it will be fine to you. These two, I mean, green colored portion I'm talking. So let me take you to the whiteboard once again. Okay, say this is my structure. And let me just remove this thing. And let me this out and let me draw that. This is the rotor and let me draw the shaft. Okay, so for example, we energize the circuit, three-phase system, and you remember then previous class I told you there will be a rotating magnetic field of the stator, which is phi s, rotating magnetic field, phi s, which is moving by 120 f over p. And assume that that is moving, for example, anti-clockwise. Magnetic field direction is anti-clockwise. Therefore, that is the expectation that finally this shaft will also move anti-clockwise. That is the expectation. So this means that this will follow the direction of this one. That is the reason I was telling you, as last class I was giving you an example that what you can do on your backyard. You can make a shape like one side is larger or much heavier than the other side. For example, you made one side much bigger. This thing, it was originally a leaf, and then you made, I mean, that type of sand, and you made a hole here. And if you put a stick here, and if you hold against the wind, definitely it will start moving in this direction because this side is heavier than this side. So that is the meaning. If you say this side is phi s, then this side is that phi r, I mean the rotor magnetic field. So that's why the actual shaft movement or rotor rotation is determined by the direction of the magnetic field of the stator. That is the meaning. Therefore, if the stator magnetic field moves clockwise, then this motor will move clockwise. If this moves anti-clockwise magnetic field, then this will move anti-clockwise. Now that is the common practice. Now for some reason, you find that, okay, my motor is rotating in opposite direction. For example, on the motor template, on the motor nameplate, in motor manual, it is mentioned that it should move clockwise. But suddenly you noticed that no, it is moving anti-clockwise. It is moving anti-clockwise. Then what you have to do? Immediately you have to stop the motor. Immediately you disconnect. Immediately you disconnect. You stop the motor. And then what you do? You just interchange any of the two lines. You connect this on here and you connect this line there. You just swipe any of the two lines. And definitely you are making connection. Or you make connection this on here and you make connection this on there. And this is as it is. You just need to interchange two lines. You just swipe any of the two lines. Then next time you will see, no, my direction of rotor is as it is, as expected, as prescribed on the manual or on the system. So therefore, while you will be doing this lab experiment number 3 and 4, you might face this issue. I mean, typically no, but sometimes it is. It depends on which machine you are using. If you notice that your motor is rotating in the opposite direction as prescribed, as suggested, then immediately you stop and then you just interchange. Therefore, can you guess what is happening with the interchange? That is the phase sequence issue. That is the phase sequence issue. Like it is somehow not matching with the proper phase sequence. So if you interchange, then your phase sequence is matched. Consequently, your magnetic field direction will be fixed. And finally, your motor direction will be corrected. So therefore, you might face this thing just to interchange two lines. That is the meaning of that, the bullet there. You see, that is the meaning I was telling. Direction of rotor rotation can be changed by interchanging connections between any two lines. And that is the first thing I told. Rotor rotates in the same direction as the stator magnetic field. Okay, then moving forward, as you see that in case of motor, that shaft movement, rotor movement, that is the main thing. From the motor, my expectation that I will get mechanical output power, I will get shaft output power that I want to utilize for various applications. For example, from the ceiling fan, that is a motor, I get air. That is my objective. Same thing for conveyor, elevator, escalator, all are the motor, and they have different applications or different objectives. So therefore, main thing is I have to control the speed. So that's why I need to know what are the methods of speed control of induction motor. So therefore, speed control of induction motor, I mean for any motor, not just induction motor, for simple DC motor, for synchronous motor or any type of motor, speed control is very important. So therefore, currently because we are dealing with three-phase induction motor, how we can control its speed. So you see, I have written down those 5 standard methods that you have to remember and then understand. So what is the first one? Frequency change. If you change the frequency, which frequency? Supply voltage frequency, which, which is the stator frequency. If you change the frequency, then your speed will change. So therefore, I am coming gradually. Pole change. If you can change the pole number, then the speed will change. So, and then why that frequency and pole thing is coming? Remember that synchronous speed equation, ns 120f over phi. ns 120f over phi. So therefore, if you can change frequency or if you can change the pole number, then your speed will be changed. Because that ns 120f over phi, that is the speed of the magnetic field, stator magnetic field. And that is the governing factor to drive the rotor shaft ultimately. Because if there would not be any magnetic field at the beginning of the operation, then there will not be any voltage build-up on the rotor circuit, no current, no torque, no interaction, no motor rotation. So that's why that ns 120 by p, if you can change that speed by controlling f or the number of pole. So number of pole means these are not the physical poles. You just need to change the winding pattern on the stator. I mean, in real practice, there are some options. Okay, you can change this amount of coil or this amount of coil. There is some options and switching. Accordingly, your pole number will be changed. Pole number could be 4, could be 6, could be 8. Accordingly, speed will change. That is the meaning. So therefore, frequency change, pole change thing, just you can realize from only that equation, ns 120f over p. Now then couple of other things. Input voltage control. So then definitely you all are aware that main input power is the input voltage to the stator or input current to the stator. So therefore, if you can control the input voltage or input current with the help of variac or by some means, if it is not fixed, if you can make it varying, then definitely your initial stator magnetic field fluxes will be reduced, rotor voltage will be reduced, torque will be reduced, speed will be reduced. I mean, think about the ceiling fan speed control. What you do, like you have 3 string. This is on speed, then second medium speed, and then the other speed. What you do basically, you control the input voltage. Therefore, by controlling the input voltage or input current, definitely you can control the speed of the induction motor. And then there are other methods. So therefore, this input voltage control from the input side, this is frequency pole in terms of magnetic field speed. But then you can go with the rotor circuit from the rotor side, rotor resistance control for wound rotor type only. You remembered that in the last class, we were discussing that there are 2 types of rotor. One is called wound rotor type. Wound rotor means there are 3-phase coils mounted on the rotor. And then other was the squirrel cage type. Squirrel cage type means it does not have coils placed on the rotor. They are just some sort of conducting bars and looks like the cage of a animal squirrel. Accordingly, it is called squirrel cage rotor. And it cannot be connected to any external resistor. But if you remember, if you see the previous class, and the picture of that wound rotor type, you can connect external resistor. And if you connect external resistor, this means that you can control the rotor current. And if you control the rotor current, meaning that you will control the rotor flux production and then interaction and ultimately the torque control. And if you can control the torque, meaning that that is the speed control. And then there is another, I mean, I will be discussing again this one, and soon I will show you one picture. And then power electronics or solid state switching based control. So therefore, this thing, number E, basically very similar to number C. In case of number C, it is just typical input voltage control, just with the help of the variac. But this is very sophisticated, very smart or the robust method with the help of power electronics. So therefore, goal of this power electronics or solid state means power electronics. Actually, sometimes you will find this keyword in literature, this book or any book. Solid state control means, or sometimes physics based control. So physics based control, solid state control or power electronic control, all are the synonymous, the same thing. So therefore, what you do with the help of power electronic circuit, basically you will be controlling the input voltage. So now the thing is that there is one equation, although today we don't have much time. Everybody see, I mean, in next class I will discuss this one in further. Torque speed characteristics of induction motor. What I have written, torque is proportionate to Vs square. Torque development in induction motor is square to the stator voltage. And you know, stator voltage is the applied voltage. And this thing is coming from this conclusion. I mean, next class I will show you how we can derive this one, mathematical derivation. What is torque is 3 over omega is, that omega is in, you know, synchronous speed, but in terms of omega, I mean in terms of radian per second. And then you see Vs squared, R2 slave, R1, you see these symbols, but then this is Vs squared. Therefore, all other things could be constant, but the main thing is the Vs squared. So that's why torque is proportional to Vs squared, meaning that the input voltage to the stator. So therefore, this relationship states the fact that if you can control the Vs, definitely your torque and speed will be controlled. So that's why when I was mentioning here that input voltage control or the number E, power electronics based control, the goal is to control this one actually, to follow this equation. So therefore, when it is like power electronics based control, I think for you just I have a circuit, this will be that picture. You see, this is the motor three phase, and this is the stator, just a stator, this is the stator. You want to apply voltage, but you see, here are the three lines, L1, L2, L3. It is not direct. It is not direct. With the help of this arrangement, this is called that this one, power electronic or solid state switching control. So what it does, everybody see, this is the input power, this is the rectifier circuit, this one. So what is the goal of the rectifier circuit? It will convert AC into DC. Therefore, this portion is DC. And there can be fluctuating DC. There could be some ripple on the DC. That's why you need a capacitor. And this capacitor is called the DC link capacitor. See this term, DC link capacitor. So, and then you will get a smooth DC, but then your motor is, you see, it is the three-phase AC system. Definitely you need AC voltage here. But then until now, this is DC. So again, you have to convert back into AC. That's why this circuit, you see, it is called inverter circuit. Inverter circuit. So therefore, there are switching devices. These devices, these could be IGBT, insulated gate bipolar transistor, or GTO, gate turn-off devices. I believe you have learned this on in electronics course. I mean 3-1 course about this IGBT or the GTO, insulated gate bipolar transistor or gate turn-off thyristor. This one, and these are the anti-parallel diodes. You know these are the diodes, anti-parallel diodes. It is written. So therefore, with this arrangement, this is very sophisticated and very robust arrangement of inverter. You can convert from DC into AC with desired amount. Therefore, in fact, for this circuit, to control, you see the switching devices, basically you have to create some sort of pulse, triggering pulse to trigger these, you see, like 1, 2, 3, 4, 5, 6, these 6 IGBT or the power electronic device. You have to produce some sort of switching pulse or switching signal. And at that time, you can control the voltage here. So therefore, this is rectifier. This is not doing anything. It is not controlling. Whatever the input voltage you are applying, accordingly, it is producing the DC voltage here. And that DC voltage, this is the amount of that DC voltage. You see, conversion from AC voltage to DC voltage, rectifier. You see, VDC 3 Vm by pi cosine of alpha. This Vm is the peak or amplitude of the AC input line voltage. And then alpha is called that the firing or triggering angle of the diode. Or if it is thyristor, then for the thyristor switch. Then by following this equation, DC voltage is produced. So that's why in this circuit, whatever the input is, with the uncontrolled rectifier, you will be getting a DC voltage here. But then the main control is here. Main controlling is the switching or the triggering pulse. That time you need sophisticated. In this class at this level, you will not study that sophisticated control. Just keep in mind there is sophisticated control system. With the help of that control, you have to control these triggering pulses. Consequently, you can significantly control the input voltage here. So therefore, goal of this arrangement is just to control the input voltage, not to apply the direct voltage there. Just to follow this one. This is my base equation that if I control the input voltage, then I control the torque and hence the speed. That is my objective. That I am doing with the help of this arrangement. And that is called this one, power electronic or solid state switching based control. Therefore, objective of C and E is the same, to control the input voltage. Everybody, could you follow me so far?
Yes, sir. I have one question about the speed control methods. Are they all like equally able to be controlled dynamically, or are some of these methods like harder? And are we also going to talk about which methods are most efficient?
Yeah, so therefore all methods can be equally applied and they can control dynamically as you are asking. But if you prefer which one is the best method or the preferred method, that is the number, the last one. The last one is the most preferred one. And number D, you will be doing in lab the number D. I mean, you will be doing both, in fact, D and E, both in the lab. So therefore,
Okay.
the most preferred one is the, or if you say the best one, that is the number E, power electronics based control. But all 5 methods can control dynamically. But this is the best, and then also this is very, I mean, well known and then preferred method, the rotor resistance control. These two basically.
Okay. Thank you.
Okay, thanks. Okay, I think we're almost 11:06. So I like to conclude here for today. Like I will continue this discussion, and also you see that I want to discuss this thing. Induction motor can work as motor, as generator, and then braking purpose. So I will be continuing this discussion in the next class. Okay, so with that, let me stop sharing. Does anybody